Hello everyone, my name is James Ryan, and today I am here to show you the look and say sequence in Haskell. So, Dushan requested a Haskell video. He said, you should show me some Haskell. So, I did get started on another Haskell video. Actually, specifically requested a tutorial. Now, wasn't ready for a tutorial quite yet, because I think that's quite a big ask, and I'd have to make sure I know what I'm talking about first. So, instead, I decided to make another video, a sort of teaser, if you will. And then that quickly escalated into a full-blown project of its own that's going to require some good editing, because the program turned out to be quite a bit bigger than I thought it would be, or take longer to make at least, which means more editing regardless of how big it is. So, consider this a teaser for the teaser. So, first of all, let's load up MS Paint for some backstory. Accessories, Paint. So, got MS Paint. What's the backstory? Well, the backstory is the look and say sequence. Kind of. So, about a year or two ago, one of my good friends, Quack, said to me, "Hey, can you guess what the next number in this sequence is?" So he showed it to me. 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 1, 2, 2, 1. Can you guess the next pattern? It's 3, 1, 2, 2, 1, 1. And then it's 1, 3, 1, 1, 2, 2, 1, 1. I mean 2, 1. And what the sequence is each next part of the sequence basically tells you what the previous sequence was. So here there's a 1, so you say 1, 1. And now there are 2 of them, so you say 2, 1. Now there's a 2 and a 1, so you say 1, 2, 1, 1, because there is 1, 2, and 1, 1. So now you say there's 1, 1, that's 11. There's 1, 2, so that's 12. And then there's 2, 1, so 2, 1. So for each... So, that's what it is. That's a look and say sequence. Now, Quark tasked me with finding a mathematical relation to describe this. As in, describe it mathematically. Not qualitatively, quantitatively, with mathematics. So I tried to come up with some complicated group set theory, not group theory, just set theory way of doing it. And somehow, I don't know how, I managed to come up with some really complicated formula that somewhat worked. Problem is only generated in reverse. So feeding in one of these numbers into this complicated formula, which was probably bullcrap anyway, not correct notation, would give you the previous number. The reason I did had to do it through such a weird way, going through set theory, was because at that time, I had a question in my head. Where do you draw the line between mathematics and computer science? Where do you draw the line between, okay, these are maths, these are functions, etc., etc., and these are algorithms. These aren't things that are constant for all time and you're doing operation. These are algorithms. You do one thing, you store things in memory, etc., etc. It was like 2 different worlds that were just somewhat related. Then I met Haskell, which kind of turned that somewhat around. And then just through time I realized, you know what? Any line drawn between mathematics and computer science is completely pretty arbitrary. half of computer science basically is mathematics. I mean, computer science is just another form of mathematics. It's just another language. And strings, while these numbers are really hard to relate mathematically just as numbers, they're quite easy to represent as strings. And functions, you can make your own functions. Using piecewise functions, I was like, well, that's kind of cheating. That's not mathematics. That's, when you put in if and else, that's algorithm. But you know what? Who cares? Piecewise function? Fine. Just shove it in. It's allowed. Who cares? So, with piecewise functions and representing these as strings, now you're saying strings, that's computer science, not mathematics. No, strings can be represented as a mathematical object in group theory. They're a monoid. What's a monoid? Well, to put it simply, monoids are objects that can be added together. And there is a group of objects where there is a defined operation such that any two of that group returns another one of that group. It doesn't necessarily have to be commutative, and it doesn't have to have an opposite either. But if that can be defined, then that is that. Strings are monoids because you can concatenate them. You can take the string hello with a space. You can take the string hello. You can take a string with a space. And you can take the string that says world with an exclamation mark at the end. And you can concatenate them all. And it will say hello world. You can't reverse that. You can't say minus world and then just end up with hello, because then you'd also have to define, well, what happens if I say minus zebra? You can't take away zebra from that. So taking away a string is not defined. It's also non-commutative. If I put them the other way around, it says world hello, which is all different. But strings are monoids, and Haskell is functional programming. So we can represent these in Haskell. How can we do it? How can we make a function that generates all the members of the look and say sequence? I'm glad you asked. Let's get started coding. So I'm going to zoom in for you guys, and now we're ready. So we're going to say let look and say. Well, what I want to do is first of all, we got to come up with some type of algorithm that translates each of these into the next one. Well, I got an algorithm in my head. What I do is I'd say, well, you start off just with nothing in particular in mind. You just see what the first number is. So the first number is 1. Okay? So now I have a number 1. Okay? I've drawn it on screen. And I say, if the next number is a 1, so I say 1. And how many 1s have there been so far? There's been 1, 1. Good. Okay? Now I say, alright. Now, if the next number is also a 1, increment the rightmost thing. Okay? Incrementing. So the next one is a 1. So I am looking at this in particular. This one in red. So if the next one is a 1, increment it. Okay. So now I have a 2. And then you look at the next one. Alright, now it's another 1. So increment that to 3. Alright, 3 it is. And let's just move this over here for clarity. Alright, now, and then I do the same thing again. So if the next one is a 1 again, increment it to 4. But if it's another number, then here's what I want you to do. I want you to replace it. I want you to replace the 1 with that number, and take this 3, 1 here, and append it to the end of your list, to another list. So what I want you to do, so the next one does happen to be 2. So take this 3, 1, put it over there, change this 3 back to 1, and replace this with the number 2. And replace. So you take that, you put it over here, change this back to 1, and replace this with 2. Okay? Simple. So next thing you need to do is just keep following that same algorithm. So the next one is a 2. So we're going to replace this one with a 2. We're going to increment it. The next one is a 1. So we copy this, append it to that other thing to those previous ones. Take this, replace that 2 with a 1 again, and replace this with another 1 as well. In Haskell, how can we represent this? Well, the way we can represent such a function is with a fold. We want to, because we took a value, we had a list of values that were empty originally. We looked at the first number and we changed the values based on it. Then we looked at the second number, and then the third, the fourth, the fifth, and so on. So we want a function that can do that with each number and then apply that to fold it. Now our function had to keep track of 3 different variables. It had to keep track of the new number it was making. It had to keep track of the amount. You'd have to keep track of the current number and the amount of the current number. Finally, we needed to find one last thing. Now that it's reached the end, it needs to know what to do when it's reached the end of the list. Well, what you do is you need to take this and append it to the last thing. Okay? So let's start making that function. So let's get started on that fold. We want to make a function, LAS, and remember we want a fold function, not some recursive function. So we're going to say that what was the storing function? What was this thing it needs to store? We take a string, we take an integer, we take a character, because we're feeding it characters, right? Because we're treating these as strings. And then we take another character, and we return another list of string int and character ready to apply to the next character. Right? Okay. So we say LAS, and the first thing we want to do is provide it with an initial edge case for when it's starting, when it's just starting. And that will be an empty string, or actually it can be for any string really. For any string, XS, when this integer is 0 and there's no character in mind, or if the character is 0, because 0 should never appear in a look and say number sequence, and the next character is X, then you want to return, you want to keep the string that you have the same, and you want to replace that with 1x. Okay? On the other hand, if you already have a character of some description in mind, instead of you not looking for anything in particular, then you have two choices. If the new character x is equal to y, then you want to keep the same string, you want to increment n by 1, and you want to keep the same y, okay? Because y is x. Okay? On the other hand, if x is different, you want to take xs and you want to append you want to append you want to take xs and then you want to append n as a number and y. Okay? Because now it's a different number. And then you want 1 and you want... So you want 0... Let me think about this. Your next thing is not y, right? So you want 1. What do you want? What do you want? Well, yeah, you want 1 and the new x, right? That's what you want. Right, yes, correct. And that should be it. And I will change this back to... well, no, we'll keep it the same, just for clarity. Okay? So that should give us that. Now, how does this work? Las empty 0 0 on 1. Oh, well, we have to load up our program first, and I've named it lookandSay.hs. But there is a problem. Line 5 couldn't match the expected type list of characters with the actual type character. Yes, yes. That is a problem. So show n and y. Just going to do some special notation here. Because it can't add y, because y is a character. But if I append y to an empty string, it will become a character. Right? So if I load this up now, it works just fine. So now I can write now I can write that, and it doesn't like it. I figured the problem. This needs to be that as well. There we go, fixed. So if I do that, it says 1 0. If I do that, it says 1 1. Good. So we're ready to start folding. Okay, so it worked. I'll just edit that part out where I completely failed to see that. So now let's try folding. We're going to fold, I think fold L means fold from the left, I hope. We're going to start with our initial empty string 0 and 0 character. And we're going to apply it to the following. 1 1 1 2 2 1. 1 1 1 2 2 1. And it doesn't work. So let's try folding. Let's oh yes, I'll probably need to, let's try folding from the right. Alright. Well, I gotta look up folds now, just to make sure I know what I'm doing. So, fold L. Fold L. Should take me to Google. Google is like the Haskell of Google. And you can type in any function, and it will give you a nice reference for it. So, fold L. Fold L applied to takes the function for, oh yes, the function goes first. That'll do, won't it? I'll cut that out too. I didn't put in the frickin' function. So I want to fold L, and it says here, fold L takes a starting value, typically the left identity, and a list, and reduces the list using the binary operator from left to right, which is exactly what we want. So we want fold L, las, then we want that 0, character 0, and then we want our number, our string 1 1 1 2 2 1, and we get 3 1 2 2 1 1. Is that what we have in this? 3 1 2 2 1 1. Oh, good, it works. Well, it appears to. The last thing we need to do is we need to have some way of extracting what we just said. And the way I'm going to do this is with a quick anonymous function, which is which is x, which is that you take a B, C, and you turn it into, oh sorry, let's just zoom in. You take A, B, C, and you turn it into the following. A plus plus, show B plus plus, show, sorry, plus plus, C, bracket bracket, da-de-da, da, da. And now we have it. 3, 1, 2, 2, 1, 1. So, in order let's get that in our thing. Let's say display this thing equals equals basically this thing, xs and y, and then you can just replace this and say display xs and y. Simple. Is xs plus show n plus y as a string. So if I take that, reload it, I can now say, and one last thing, I want to make another function which is called look and say, which will be our final function, and it will just take a string. Look and say string is equal to alias 000 string is equal to display alias 000 x string. And now if I load look and say, not in scope XS, that would be a problem, wouldn't it? There we go. It all works, and now I can say look and say 1. Oh, look and say 1. Shit. Look. Oh. Equals, sorry, not display that, it's equals fold L last string. That was what we did, right? Fold L last string. Yeah, it was fold L last that string. So if I am right and I load look and say, I can say look and say 1, and it gives me 1 1. I can say look and say 1 1. It gives me 2 1, etc., etc. And so the next, what I should be able to do, I should be able to take the first, say, 20 terms, or say take the first 20 terms of look and say iterate look and say on 1. My gosh. What's the first? Okay, that might be a bit much. Let's just take a look at the first 5 terms. 1 1 1 2 1 1 2 2 1 1 1 1 2 2 1. Oh my gosh, we've done it. Let's take a look at the first 8 terms. 1 11 21 1 2 1 1 1. Then we got 3 1 2 2 1 1. Was that what we had here? 3 1 2 2 1 1. Yes, and then we're looking for 1 3 1 1 2 2 2 1. And that's what we got. 1 3 1 1 2 2 2 1. We've done it. we've made the look and say sequence, and we can keep going. We can even just take. We can just iterate look and say one, and then we can even just take whichever one. So let's take a look at the 15th value. Good. And the 100th. Oh, that'll take a bit of time to compute. Don't worry, it'll get there eventually. I hope. Is this a function of n squared? Maybe I should probably pause that. Alright. Let's take a look at the 20th. Okay, the 25th. Alright, the 30th. The 30th is taking a bit. 31st. 35th. Yeah, that's taken a long time. There's no way it's going to be able to do 100 if 35 takes that long. Let's just see how long it takes for 35. There we go. Still going? Good boy. Good job. So there you have it, the 35th term of the look and say sequence. If I just there we go. So if you just look from this little blue line here to, you know what, let's just look at it from scratch. I'm gonna load it from scratch, okay? I bet you've always wanted to know what the 35th term of the look and say sequence was. I mean, it's on your bucket list, right? So look and say, no wait, you've got to iterate, look and say, 1, 35th. Technically it's the 36th term, because if I look and say 0, it'll give me 1. If I look and say 1, it'll give me 1, 1. So really it's the 36th term. So I bet you've always wanted to see the 36th term of the look and say sequence. Here it is. We'll just give it some time to compute, because it's a big number. It's a big number, but for you, the computer will do anything. There it is. It's going. It's going. It's writing it all for you. Oh, it's writing so many numbers. Oh, but it's too big. It's writing it quite fast. Still going. There we go. It's written it all out for you. So it's too big. There you go. So if you can see that, that is the 36th term of the look and say sequence on the screen in its entirety. It might be a bit too small for you to see on your computer, so I'll zoom in for you, just so you can take a look. There you go. Some nice little patterns appearing, some diamonds and stuff, you know? Maybe that's just my brain. It's pattern recognition going into overdrive, seeing patterns where there are none. Well, now they're mountains. Nice. So yeah, there you go. Analyze it, look at it, put it in a book, print it out, whatever you want. So there you go. That's functional programming with the look and say sequence. My name is James Ryan, and I have been your host. You've been watching Cerebrosplosion. I hope you have a good day. Don't forget to be awesome. That's what the nerd fighters say. Be good. Yeah, and just try to do something. Try to don't just consume content, create it. That's what I'm doing. Thank you. Peace out. Is that what I say? I don't even know where peace out came from. This is like something I don't even say at all, except for in these videos. Alright. See you guys. Ndilshan. I hope you enjoyed this video. Remember to like, favorite, and subscribe to all my channels. I only have one, so that should be an easy task. I don't know how you're going to like my channel or favorite it, but you can definitely subscribe to my channel and like and favorite this video. Liking and favoriting all my videos though might be a bit of a big task, so I won't give that task to you, because that would just be mean. See you guys, bye!